Hello, and welcome back. Today I'll be going over implementing the colliders and contact detector from the previous video. I did mean to have this out sooner, however I ran into some loose ends which I neglected and they needed to be resolved. Now looking at the code here, this is basically a skeleton of the contact detector that's going to be built up to. And at first glance, in the contact detector structure, you'll notice that the colliders themselves aren't actually stored, but just BVHs. And if you look over here at the BVH node, this is where the reference is stored. And it can be either a non-resizable container or an address to a non-resizable container or some dynamically allocated memory, which I do want to make a quick side tangent about. Generally, dynamically allocating memory is referred to as something that should be avoided, especially in games, because it has to wait for the operating system. And this is true, however, it's not the only case which dynamic allocation can be performed. If the memory for the application is already reserved at the beginning of the program, then you can allocate out of a private memory pool and you don't have to wait for the operating system. In C++, you can use placement new, custom allocators, and containers to turn the more sporadic object locations into something hopefully more linear. And in the future, I'll be circling back around to the memory allocator as the prior implementation was just for testing other parts of the framework. But besides that, the point of this video, for the rest of it, I'll be focusing solely on the colliders and interfacing with them in this contact detector. Okay, so now let's look at the collider and the geometries that will be supported. The idea for supporting these four shapes here comes from Dirk's GDC talk about generating contact points. Now, if you recall, the ultimate goal is to generate a collider object, which can be used with any of these four shapes, and then be used generically throughout the collision detection pipeline. And the way we'll do that, left a little note here, will be through type extraction. And to do this, we're going to leverage a base class, or in this case, struct called collision volume, which will be inherited by a templated structure called collider geometry. And now here in the collider itself, we'll store a pointer to a collision volume, as well as a ID to the physics object. And I actually forgot, but here in the collider geometry, we want to store the geometry itself, and this will be one of these four shapes that get passed in as the template argument, and the constructors, which we can go ahead and make now. And so there's going to be two constructors. The first will just be the generic default constructor, and the second will be a templated constructor which mirrors, I can never spell this word, which mirrors the collider geometry. And the reason for this is I wanted to give the ability to set this collision volume either when you create the collider or when you or you can delay that choice. I'm sorry. It's going to finish typing of this, and we'll also have a deconstructor, but we'll look at that later when I hop into Manifest. Right now, I just want to go over a quick little implementation of this, and then I'll show the actual integration and working with it in the project itself. So from here, we're going to want some way to get and set the collider. And here in set collider, you can kind of see what I was talking about before, where if you want to delay creating this collision volume, you just want to create, say, a vector of collider objects, and you don't want to attach anything to them yet, then you can later you can defer that option and just call set collider and pass in the specific shapes that you would like. And then to get the collider, very simple, you just query the collision volume. And this function is actually one of the things I was alluding to in the theory video about how you can easily blow up your code. And the reason for that is, as I believe, there's really no way of getting around some of these problems because they're logical problems. So it's really just about how you want to organize and solve that problem. And I have one more typo, fix that real quick. Actually, there's another typo, because that shouldn't be a collider. It should be creating a collider geometry. And this is actually where the type extraction comes into play, by the way. Because if you see here, collision volume is of type collision volume, but what we're really always going to be creating is some collider geometry that should get stored into this pointer. And now we can almost use our colliders. In fact, they're actually all set to be created and stored. We should be able to go here into main and do a little test that I wrote, and if everything went through fine, should compile. Okay. Initializer list. Okay, so yeah, as I said, have to match the constructors. So we'll have the default one for deferring, and then we'll have the templated one for creating our geometry. And I believe that should geometry, yeah, that should be fine. So let's try and run that again. And there we go. We see 2, and we have 2 there. Although now we need to address the next problem of we can't actually use these because we can't get this information back yet. We don't actually know that this collider is a sphere and this collider is a hole. So let's go ahead and address that problem now. To do this, I kind of alluded to it when discussing the theory that the shape was going to now be implicit somehow. And yes, the collider or the collider geometry will be storing an actual collider object. That's not really what the collider is concerned with. The collider is more concerned about knowing generically what kind of geometry it is. And so to do this, I'm going to use an enum class called underlying geometry. And this will just simply store another copy of all the names of our shapes that we have. And then something simply to, catch an error. Although, and this will be made a little bit more clear in future videos, the values of these are all to the power of 2. So it's 2, but through the powers. So sphere, this is 2 to the 0. I can find the key. 2 to the first, 2 to the second, and so on. And yes, this will be used for bit codes later on. It's not too important now, but that's why they get the distinction they do. And because, like I said, the collider, there we go. The collider wants to be able to quickly know what type of collider geometry it needs to reinterpret its cast into. We're going to want to store the underlying geometry inside of the collision volume pointer itself. Because even though the collision volume is going to be turned into collider geometry, because the collider geometry itself is the collision volume, we'll still be able to query this variable out of this pointer. And now this just leaves us with one more problem of how do we actually set the underlying type. And we'd ideally like to not have to add on any extra work to the programmer, and luckily we don't have to. Since whenever we're creating a collision volume, we're creating it inside of a collider geometry, we can go ahead and hijack the creation process of this, and we can use in a specialized function the actual templated object type of geometry to return the proper enum. And that's going to look a little something like this. Just going to copy over the function. And so what this does is, oh, I guess I called it differently. Yeah, so what this function does is it just simply gets given the type T and then checks if the template type that we've been given is one of these four shapes, and depending on which it is, or I guess if it's none of them, it returns the proper enum. And so we just go ahead and create a constructor for this. And we'll pass this on. All right, and so now we should be able to create the collision volume. And here we can go ahead and do select type, geometry. And once more, everything should compile. No, we have bugs. Undeclared. Oh, right. In these are all something slightly. Oh, I guess capsule. These are all names slightly different. I just put these together real quick for the sake of presentation. Okay, so that. No. Give me 1 second. All right, so it was just the arrangement. The colliders had to be defined before this function, as well as there's one more bug I spotted. The geometry wasn't actually being passed into the collision volume. But now everything should work out fine. And in fact, we'll set a breakpoint here. Or try it again. Set a breakpoint. And if we look here, don't know if it'll come up on the debugger, but collider 1 is a hull, which is correct. And collider 0 is a sphere, which is correct. All right, now that we're all set with our colliders, we can quickly take a peek about how they might be used in the pipeline. The first thing we probably want to do is insert our colliders. So to do this, we will simply check if the collider is marked dynamic. If it's dynamic, we'll put it into the dynamic colliders. And if it is, oh, why doesn't it like that? Good old IntelliSense, no problem. And if it's static, or if it's not dynamic, we assume it's static, and simply put it in there. Very easy. Next, we probably want to be able to remove the collider. And again, we would just have some remove collider function. And in this one, we're not actually going to be passing in the collider, but rather we'll be passing in the physics ID. And the reason for this is because the collider gets stored with a node, we need to, when that's created, track the index that node is created at. If we can track the index, then we can simply reference the node in here, and then we can get back our collider and this node and clean them both up in one shot. And to do that, it might look something like this. We get the node index from the, oh well, first we need to determine which BVH it is. And we just simply again say if it's dynamic, it'll be the dynamic colliders. If it's not, it'll just be static colliders. So from there, we're gonna want to query that BVH's collider node map, and we're gonna want to give it the ID. And then now we can go ahead and get that node. Sorry, this should actually just be remove node. And it'll take in the BVH node. I mean, it doesn't really matter because this is all pseudocode, but for clarity's sake, let's do the node. And so we just go to BVH nodes, the node index. We would want to get our collider. And I don't actually think you can make a constant. And then we will remove the node and delete the collider. Oh, because it needs BVH as well. And just like that, that's how we can insert and remove. The only thing left to do is update. So you only really need to update your dynamic colliders because static, as the name suggests, can never move. And this isn't the actual update loop that will be used in the framework, but right now I'm just showing the how you would kind of query your colliders. Because if you remember, we have to go through the collision volume. So we'll go ahead and get the body's ID, get the node index for the body from the map. And then from there, we would get our collider. Well, we can go ahead and get the node. So the body node. And then now we can get our collider. All right, and then now we can simply check through a switch statement on the collider what the collision volume is. And we'll actually need the underlying geometry. All right, and now we only need to check for if it's a sphere, if it's a capsule, or if it's a hull. And the reason for this is meshes will always be static, so there's no point in ever doing that check here. And now we just can kind of maybe do an update like this, where we say collider, get collider geometry, and that way we know it's a sphere. We can just reinterpret it as a sphere. Same thing here with capsule. We know it's a capsule. And same with hull. And so just like that, we can very easily do our collision detection pipeline more or less with these very generic colliders. And then now I'm going to hop into Manifest real quick and just briefly go over the entire contact detector and then just show a little collision of a hull and a sphere for proof's sake. Alrighty, so taking a look here in the framework, we'll start with the collider deconstructor. Really, this comment says it all, but basically we can't just delete the collision volume and be done with it because our hulls potentially have allocated memory they need to return. So here in the Collider Geometry Deconstructor, we make a check that if the geometry type is a hull, we call the deallocate method on its memory, and then we're good to continue on. The rest of the geometries don't need this check since they live entirely on the Collider Geometries stack. Next, I want to look at the contact detector itself. Here you'll see it's generally the same thing as in the mockup, however there's a third BVH for terrain colliders. This is because the terrain itself is basically an acceleration structure and an acceleration structure. So they get their own container for collisions to keep BVH bounds nice and uniform. And last but not least, we'll take a look at the collision detection pipeline. So we first start with the update to our colliders. Here we basically have the same code as before. The major difference is here in the BVH, instead of using a map, I use a container that is essentially still a map. However, instead of storing pairwise, it stores them in parallel. This allows a linear search to be done over the keys and then retrieve the exact index of the mapped object. Either way is fine really, both have their advantages and disadvantages. After updating the colliders, we go ahead and perform the 3 collision detection phases. And these phases I'll dedicate an entire video or probably multiple videos to, but for now we'll see that the interface for the colliders allows the detection process to be rather trivial. In broad phase, we just check BVHs against internal and external nodes. In the mid phase, we check if any broad phase contacts are with a mesh collider. If so, we perform an intermediate check for collisions with the mesh octree and the non-mesh collider. And finally, in the narrow phase, we check the actual underlying geometries for collisions using a series of overlap functions. But yeah, that's just about it for the collision detection pipeline and the colliders. And now, to prove that these things actually work, I'll go ahead and show a few collision tests and we can see just how flexible the detector can be. Alrighty, so first up is a simple test between 2 sphere objects. Go ahead and copy that, paste it, build and run, and we can see works just fine. The next test is going to be between 2 capsules, capsule 1 and capsule 2. And if you're wondering, by the way, how these colliders are being determined, it's right here. A collider of shape 0 is a sphere, shape 1 is a capsule, shape 2 is a hull, and then shape 3 is a terrain mesh. But nonetheless, 2 capsule test, build and run. And they even have capsule stacking. And then the third test, which is my personal favorite, is between 4 spheres and a capsule, which is kind of shot down like logs on a river. And then last but certainly not least is a test between two hulls where one is spinning on top of the other. And that should just be about it. Thank you all for your time. Thank you for watching. If you feel like I missed anything or need anything explained, feel free to leave it down below. And I will see you in the next one.